Okay, so in this last proof video, I'm going to combine everything we know so far to get to the final answer, and the final answer is what happens at time infinity. So that's f of x theta infinity, and the result we want to show is that its expected value is this thing in terms of the kernel k. It's k of x training data times k of x inverse times training labels. So this is an nx by 1 vector. This is an nx by nx matrix that got inverted, and this is a 1 by nx row vector. And so that multiplied all together, the kernel k contains all the information about the features, and the vector x contains all the training inputs, the vector y contains all the training outputs, and you combine them like this, that tells you on average what happens after training. So that's one thing, and we also want its variance. Its variance, so it turns out it's Gaussian, and its variance is equal to the following: k of xx minus k of x script x, k of script x, k of script x, lowercase x. So this is a nx by 1. This is an nx by nx. This is a 1 by nx. And this is a 1 by 1. And that gives you the variance. And you can do the same thing with any size vector. You can get its covariance, and that's because f of x theta infinity is actually going to be a Gaussian process. So for any finite collection of points, x1, x2, x3, f of f at those points after training will be Gaussian, and its mean will be given by this thing. Let's call this thing m of x, and let's call this thing all right, I got to write it again. Let's make a new function. Let's make a sigma of xx prime. We're going to make the same thing, k of x prime minus k of x, k of script x, k of script x prime. So we'll call that thing sigma. We'll call this thing m of x, and f of x theta infinity is going to be a Gaussian process with mean m of x and covariance sigma xx prime. So that means for any finite collection of points that you have, if you look at the vector made by those points, f of x1, f of x2, f of x3, it's going to be Gaussian. It's going to be a Gaussian vector whose mean is given by this guy and whose covariance matrix is given by this guy, sigma of x prime, in this way. So how do we know that? Why is this true? And actually, we've done almost all the work already, so this is not a surprising result. So this is Theorem 9 in the notes. And Theorem 9 just combines, if you take Theorem 7, or is it Theorem 6? Proposition 7. Yeah, Proposition 7 and Theorem 6. So Theorem 6 says f of x theta infinity equals some explicit thing involving f of x theta 0. And Proposition 7 says, by the way, f of x theta 0 is a Gaussian process of mean 0 and covariance k. And if you combine these two things, so this is an explicit formula, and this tells you explicitly what happens at initialization. You combine them, you get Theorem 9. So that's the short version. Here's really how you do it. So to do it, I'm going to apply Proposition 7 to get the distribution of this vector. So I'm going to look at the point f of x, and I'm also going to look at all the training data. So I'm going to look at this nx plus 1 vector, f of x theta 0, and then I'm going to stack f of x theta 0. So this is a vector of size r to the n x plus 1, where the top row is the vector we're interested in, f of x theta 0. Sorry, the top row is the point we're interested in. And down here is a vector of size nx, which is all the training points. And by Proposition 7, this thing is a Gaussian. So by Prop 7, we get this thing has mean 0. That's always true, and it has the following covariance structure. So I'm going to write down the covariance. What's the covariance? It's going to be a matrix. It has this matrix k of xx, which is a 1 by 1 matrix. Then here you have k of x, big X, k of big X, little x. I feel like those are backwards. Yes. No, those are right. Okay. K of xx. So this is an nx plus 1 by nx plus 1 matrix. I'm writing it in block form. where this is an nx by nx matrix. This is a 1 by 1 matrix. This is a 1 by nx matrix. And this is an nx by 1 matrix. So that's the block, this is the block version of the covariance matrix. And that's what it is at initialization. And finally, we can write the vector, this is the key point, we can write the vector f of x theta infinity and f of script x theta infinity. We can write this as a linear combination of what it is at initialization. And this is just because of theorem 6. So theorem 6. So why am I messing about with this funny vector? The whole point is that theorem 6 tells you what is the distribution at time infinity, but it depends on this guy and this guy. So it depends both on the initial value at the point x and at all the training points. So by looking at this stacked vector, which contains both, I know its covariance, I know what it is in terms of itself, and then I can just use the matrix multiplication rules for Gaussian vectors to get the result that I want. So I'm just going to fill in what this transformation is. So by theorem 6, if you read it this way, what does it say? It says at time infinity, what is it? So there's a big matrix here. It's 1, 0, 0, minus k of x, x, k inverse of x, x. Okay, and this is, again, this 0 is actually a matrix. It's the nx by nx 0 matrix. Maybe I'll write it like this. This is a block matrix multiplication. Nx by 1. This thing is a 1 by 1 number, and this thing is a 1 by nx matrix altogether. So it's this plus this shift plus k of x, x, k inverse of x, x times y, 0. Okay, this is an nx by 1 vector, and this is a 1 by 1 number. Okay, so what have we done? We've taken this stacked vector, which includes the point we're interested in, f of x theta 0, and all the training data, f of script x theta 0, and it stacks it all into one big vector. And the point is that that big vector is entirely determined at time infinity in terms of as a linear combination of what it is at time 0. So by stacking in all the training data, we made a closed linear system. That was the secret idea here. So make a closed linear system where what happens at time infinity depends only on what happens at time 0. That's why we had to include all the training data inside our system. Okay, so this is a matrix multiplication with a shift. At time 0, by proposition 7, at time 0, we have a Gaussian system. So we're taking a Gaussian system, we're applying a matrix multiplication to it and a shift. And we know from the same fact we used before, I think fact 16 or something like that, fact 17, that Gaussians, when you multiply them by matrices, are still Gaussian. So, you know, at the end of the day, you're going to get a Gaussian. We're going to get f of x. This stacked vector is going to be a big Gaussian vector, and we're going to have its covariance exactly. And there's a big matrix multiplication you have to do, so I'm not going to do it in detail. I think you should look at the notes. So it's a big ugly thing. Maybe you can see it there. A big matrix multiplication. So look in the notes for that if you want to see the details. But if you work out the matrix multiplication, you get exactly the result. And the result is nice because it tells you exactly what happens on average, the expected value and variance after training.